In the name of Allah, the Beneficent, the Merciful, Maxewell stress tensor. That is our topic. Maxwell stress tensor is an important tensor that you come across in physics. To understand it mathematically and conceptually, students must have some knowledge of certain things, of which two are very important. One is, number one, a vector identity, an identity which is namely E cross del cross E is equal to 1 by 2 del E cross minus del dot E E. Second is an elementary knowledge of tensors. So in part first we will prepare ground for your further study of Maxwell stress tensor, that's MST, or MST what you call it in short terms. Now let us first go to vector identity. Vector identity. You are familiar with, perhaps you are familiar with vector triple product, that is A cross B cross C, which is equal to, you have that famous rule of back minus cab. Back means B A C, cab means minus cab C A B. Now what is this whole thing is? This is a vector because this cross product of two vectors, hence these two must be vectors. Now the first B here, the first is a vector, so is the first here is a vector. Now the next two, they are vectors but they have a dot between them, so this A dot C is a scalar quantity. Scalar into vector, that is vector. Scalar into vector, vector in dot vector is a scalar, so you have C dot is this. If we apply now this vector triple product to these vectors, if we put A equal to E, first vector E, second vector is B, that's equal to del, and third vector E is equal to C equal to E. Here you will get a result that is wrong. You will get E cross B del, E cross del cross C is E, that will be equal to, according to this back minus cab, this formula, it will be B will be del dot A dot C, that is A E dot C, E dot E minus C is E dot A dot B, A is E dot B is del. Now this is wrong because you get del E square here. Del E dot E is E square, this is E square, while as correct formula is you have 1 by 2 del E square. 1 by 2 del E square. I have written this slightly wrongly. It is better to write it here because E dot del is to be multiplied with this. Okay. Now you have the main problem is with this term. You have 1 by 2 and you have here no 1 by 2. Why doesn't this vector triple product yield the correct result? The reason is that in this vector triple product, this is not quite vector triple product, because E are vectors, but del is an operator. Because of its operator nature, the result that you get will not be correct. So how to establish this formula? How to establish it? The easy way is ab initio. And for ab initio, we will simplify the procedure to a large extent if we just realize this thing. If two vectors have x component equal to x component, their x components are equal, their y components are equal, a and b are two vectors, their z components are equal, then a is equal to b. So if two vectors have all the components equal, corresponding components, then they are equal. So what we do, we will start with this. E cross, we'll start with this and this. We will equate these two, we will prove this for x component only. Y and z will follow the suit. So simple. Let us take the x component first. Let us take del cross E. It is not del cross E. Sorry, it is E cross del cross E. E cross del cross E. X component, it is x component. Now for that, we must realize one thing. We must keep that thing. In fact, we must keep that thing in mind. That will make it quite simple for us, quite easy for us. What is that? You just have to keep this thing in mind, that if you have A cross B, okay, then cross product between two vectors, then this is equal to, in determinant form, it is easy to remember it in determinant form, ijk ax ay az bx by bz. Now when you expand it, you take I, then I, that is x component, ay bz minus az by, one thing. Then second, jth component plus j. We can take minus j if we follow rules of this determinant expansion. We have to take minus j, but then we overcome that problem by starting with product from this in this direction. We take this product first, then this product. So bx ax, it is bx az minus b, this is ax bz, then lastly k is, kth component is, that is ax by minus ay bx. We have to note a few things. That is, suppose you are looking for x component of the cross product of these two vectors, x component. Now x component contains everything, all the things except x. There is no term here that has x, that is an x component. Ay, bz, az, by, no ax, no bx. So when you are speaking about x component, cross product yields you combinations of y and z. And when you are speaking about this y component, now see, y component, cross product yields you x and z. When you speak of z component, cross product yields you xy. So the component that you are looking for is not in the expression. That is not in the expression. Of course, that is outside in this form. In this, it is I, j, k, but not in this expression. That makes us easy to write this component. Let us follow this suit here. You want x component of E and this. Now, this is the first vector A here. This both taken together are the second vector B. A or A and B. They are the second vector A and B. Okay. Now, if you want x component, we can write instead of x component, I can write I there. That will be equal to. You can now see from yourself. It will be y component of the first vector, y component of A first vector, z component of second vector, y component of first vector EY, z component of second vector, that del cross E z component. And there is no cross dot here because these are components and components are scalars. You can multiply scalars like numbers. That is one minus then another minus AZ BY. Now you have now Z component. This is Z component BY del cross E Y. I hope this is quite clear. Now next we will repeat this for this now. Now let us consider this del cross E, this cross product, del cross E. Here first vector is del, second vector is E. So we have EY is equal to, since you are looking for Z component of del cross E, Z component of del cross E. Now see Z component of del cross E, A cross B, instead of A cross B, you have del cross E. Now that is x component of the first vector, that is del x. Y component of the second vector, that is EY, minus y component of the first vector, del y. X component of the second vector, that is EX, minus. Then you have EZ. Repeat the same for this. You have del cross E. That is y component. Now go to y component. That is x component of the second vector. X component of the second vector, that is EX, and Z component of the first, del Z. X component of the second vector, EX, minus x component of the first vector, that is del X. Y component of the second vector, that is Z component of the second vector, that is EY. Then I have simply been guided by this expression. You can do it at your leisure. You can take time. You can satisfy yourself. You must be proficient in mathematics. A student needs to be extremely proficient in mathematics if he wishes to understand what physics is. Now we can then write it as EY. This can be written as del by del X. X component of this EY minus del by del Y EX minus EZ del by del Z EX minus del by del Z del X EY. I don't think there is anything worth cancellation. Not at all. No, nothing. So please let us write equation first for it. We now go to left hand side. Let us go to this term, this left hand side. That is 1 by 2 del E square minus del dot E into E. We have left hand side. 1 by 2, of course it is 1 by 2 del E square minus del dot E Okay. Now as far as this is concerned, E square, E square is a scalar quantity. E square is simply ex square plus ey square plus ez square. Three components of E, they combine by an extended Pythagoras theorem to yield you this. Now all of them are scalars. None of them is a vector. There is no question of calling what is the direction of this, what is the direction. None of them has a direction. Direction here is present here. You have say del E square. This means you have I del by del x. I am writing this explicitly. J del by del y plus k del by del z. Now, this will yield you x component. This will yield you y component. This will yield you z component when they operate on E square. I am interested only on x component. I want only x component. So if I write x component of left hand side, that will be x component of this into x component of this, of course. Let us first take x component of this. Therefore left hand side, x component of left hand side is equal to 1 by 2. No, sorry, it is it is 1 by 2. Yes, 1 by 2 del E square. Now you want del E square. This I del by del x, j del by del y, k del by del z is del. Now put E square here, put E square here, put E square here. Now differentiate. You have 2e x, it is E square, it is ex, it is actually ex square plus ey square plus ez square. E square instead of E square is correct, but when I write in place of E square, I write ex square plus ey square. This. Similarly, I have to write it here: ex square plus ey square plus ez square. Similarly, I have to write it here: e square ex square plus ey square plus ez square. Since I am interested only in x component, I need not bother about this term at all. So I am having only this term. I have to differentiate this with respect to x. So I will get 2ex del ex by del x. Similarly, 2ey del ey by del x plus 2 del by del x, 2 ez del by del x ez. You may be thinking, why is sir differentiating ey with respect to x? Yes, we have studied before this, we have studied curl and circulation, and you saw there that an electric field which is directed in y direction can change with x. So there is rate of change with respect to x need not be zero. No guarantee about that. Now we will do one more thing. That is, we will take this 2 common and cancel it with this. We have I have still to write this part of the, that is minus del E. Now del E, just keep it there for a minute. Del E into E. E is simply I ex j ey k ez. Now you have ex del ex by del x plus ey del ey by del x del ez, then del ez by del x. Now is handle the second part, that is minus E dot del. E dot del, as you know, is ex plus jey plus kez dot del. Del is I del by del x plus j del by del y plus k del by del z by del z. This is dot product between these two, and then we have then multiplied by this factor I ex plus j ey plus k ez. That is E. Okay. Now, let us first handle dot product. We write ex del ex. First is ex del ex by del x plus ey del ey by del x plus ez del ez by del x minus. Now minus. Okay. Dot. First, let us go for dot product of these. This will be I will go with I ex del by del x plus ey del by del y plus ez del by del z. Now multiplied by I ex plus j ey. I mean this j ey plus k ez. Further, we let this operate on this. This will give us ex del ex by del x plus ey del ey ex del by del x. No, sorry. This part is from that 1 by 2 del e square, which I am writing right now. Ex del ex by del x ey del ey by del x plus ez del ez by del x minus. Now ex del by del x will operate on these three. When it operates on this first term, let this ex, I will underline this and I will underline that. When this ex del by del x operates on this, you get a term that has I, that's x, it is directed in x direction I, and it has, we can write that I here, then it has this ex, okay, del by del x, ex, this del ex by del x. Since we are interested only in x components, so we need to look here between this operator and this. Look only for those terms which are in x direction. Now this, when you suppose we start with multiplying, since one more thing, since this is a type of scalar, this is scalar, and when you multiply it with this, you will multiply this first with this term, then this whole will be multiplied with this term, then this whole will be multiplied by this term. Now when you multiply it with this term, you get ex del by del x ex, first term, that has I. Or there, which other terms will have I? Yes, see, when you multiply ex del by del x with this term, you will get a j term. When you multiply ex del by del x with this term, you get a k term. Those are not what I am looking for. I am looking only for I terms. Now come to this. When you multiply this with this, you will get another I term. Now that will have I minus I. This minus is this common minus. Minus I j, no, not j, sorry, I, this term with this term. I will show you like this. This term and this term, they will produce I. You will have ey del ex by del y. Then when you multiply ez with this, ez with ex, you will get another term minus another I term del ex by del z. Rest of the terms will be having y and z components. They are not needed. So finally, there is no need to write I here. because you are talking about x component, no need, you have already written it here, x component, no need to write now this I here. Now you have this, you can combine this term and this term will go. You are left with Ey del Ey by del x minus this and this minus Ey common del Ex by del y plus between these two terms. This is Ez here. It is Ez here, Ex, Ey, Ez. Ez here, you can check it here. Ez into this, Ez here, Ez, and then you have del Ez by del x minus del Ex by del z. Now compare it with right hand side, x component of right hand side. Let us first write it here. I'm sorry. Right hand side, you might be, you have that with you, that is simply the same as this. You can check, you will find same as this is there. So what you have done, you have proved right hand side, x component of right hand side is equal to x component of left hand side. So x components are equal. In the same manner, you can equate, you can show that their y components are equal, the z components are equal. That means the two sides are equal. Therefore, we have established that this identity E cross del cross E, E cross del cross E is equal to, that is equal to 1 by 2 del E squared minus del dot E dot del rather, E dot del E dot del E. This is that vector identity which I was speaking about. This we will be using in Maxewell stress tensor. We next have tensors. That is our main topic, tensors. So what is a tensor? There are many ways of approaching tensor study. The most popular in physics and mathematics is coordinate transformation, but we will not go for that. That is a little bit involved, complicated, and we don't have that much of time. And the simplest is tensor as an array of numbers. This simplest version, that is, of course, different versions are equivalent. Now this array, this version is most popular, most widely used in machine learning, and we will start with this, but add to it some solid foundation from the world of physics through examples of tensors, so that you don't find things abstract. It will be my endeavor to make things as simple as possible for you. I assume that you don't have any prior knowledge about tensors. So we start with this. Suppose you have a vector, say velocity vector. It has three components, Vx, Vy, Vz. Now, you want to label these components. You know, index here, subscript is x, subscript is y, subscript is z. There is a subscript on each component, and that subscript is a variable. It changes. We show it with I. We call it I, Vi, where I is equal to x, y, z. We call it index. We say that you need one index to represent a vector component, to represent components of a vector. That is vector. You need one index. There are things which require more than one index. And there is one thing that does not require an index at all. For example, let us take this. Suppose you have a lot of numbers. Say you have just start with only one number. Say 5. You have 5. You want to show it As an array, you show it like this. Suppose you have two numbers, 5 and 3. You can show it, arrange them as 5, 3. Or you can show them as column 5, 3. That's your choice. But what is important that here you don't need any dimension to represent this. I will explain that. You need one dimension. You are represent these numbers along one dimension, and here also one dimension. Let us without in order to avoid confusion, let us first go to horizontal dimension. Now suppose you have a lot of size numbers 5, 3, 4, 2, 1, 7, 8, 10, etc. If you arrange these numbers in two dimensions, you can arrange them in two dimensions. Suppose you put some numbers like this 5, 3, 5, 4, 1, 2, 3, 4, 0, etc. And this arrangement utilizes two dimensions. Numbers are arranged in two dimensions. You can similarly think of arranging numbers in three dimensions. Third dimension would be in space here, for example, a cube. And then you can then think of fourth dimension, fifth dimensions. There are millions of dimensions that we come across in machine learning. And how do we think about those dimensions? No one is able to think about more than three dimensions. We all leave to mathematics. Mathematics comes to our rescue in such situations. We believe in it, and we believe that what mathematicians actually are saying, that is correct, that is valid. Now, okay, then this arrangement, this array, these number arrays are called tensors. People call them tensors. In machine learning, at least, tensors. So we say that we have a one-dimensional tensor. If there is a single number, we say that it's a zero-dimensional tensor because it can be represented by a point. This needs a line. You have 5 here, 3 here. It needs a line. This needs a plane, and so on. So zero-dimensional tensor, we say it is a tensor of zero order. Some people call it rank, although rank and order are slightly different. Not slightly different, they are different. But then there are people who interchangeably use them, but we won't do that. We'll continue with order for this. Now, we say that we need one index. We need one index to represent these numbers. The index will have value 1 for this, value and another value for this. But we don't need any index at all. It is only one value. So this will not change at all. This scalar, such a scalar, is said to be tensor of zero order. It is zero order. That means it does not need any index to represent it. Now come to vector. Vector has at least one this index. At least not, it has one, exactly one. It needs one tensor. These components of a vector are like, for example, Vx, Vy, Vz. It needs just one index, and we represent it as T. If T means tensor, then we represent it Ti, where I is equal to, of course, X, Y, Z. This is a vector. So vector 2 is a special case of a tensor. It is said to be tensor of first order because of this one index. Then you have matrix, and in matrix you need two indices, one along the row, another along the column, and you have tensor. We call this tensor of second order. Similarly, you have tensors of third order, tensors of fourth order, and so on. We will take up examples of two tensors. That will, by those examples, we'll be able to appreciate why this concept has crept in physics. Where from? Is there anything in nature that is like mathematician's tensor? Yes, of course. There are many, many things. We will cite only two because those are simple to discuss and those we need. Tensors. One is, for example, suppose we start with this. We start with this. Suppose you have a piece of graphite. You must have heard that graphite consists of layers of carbon atoms, one upon the other. One layer upon the other layer. These are graphite. Say, look at these carbon atoms. Carbon atoms in this. These carbon atoms are bonded by strong covalent bonds. That means carbon atoms within one layer are strongly bonded to each other, but carbon atoms in one layer are weakly bonded to carbon atoms in another layer. These weak bonds are those van der Waals bonds you might have heard. Van der Waals interaction. So this bond is weak, this bond is strong. If now you pull this sheet from this side and this side, it will be difficult to break it. But if you pull the same sheet in this direction and in this direction, pull them in this direction, it will be easier to separate them. What do we learn? We learn that in substances, bond strength can change with direction. And that has some consequences. One consequence is, suppose you have, but before that, suppose you have an atom. Okay, its nucleus is there, that is center of its positive charge, its electron cloud is here, center of that electron cloud has its center of location, right, and in the nucleus. But when this atom is placed in an electric field like this, the atom is elongated in shape. Positive and this nucleus is pushed downward towards the left, towards right, and negative towards the right. As a result, there is a separation between this positive charge and negative charge that creates a dipole moment. Now, when you place a number of atoms in an electric field, those atoms are polarized. Polarized means their negative and positive charge centers are separated. Now, this polarization is approximately directly proportional to the applied electric field, especially at low these electric field values. Now, then we say P polarization is equal to some constant of proportionality. We write alpha for that, E. Now, constant of proportionality, of course, will tell us how easy an atom can be polarized. If it is easier to polarize, then constant of proportionality for it is larger. And if it is difficult, then it is, of course, smaller. Now, suppose you have an electric field in this direction, E1 electric field, and you apply it to a crystal, to a substance, say something like this. You have a substance like this, and you apply it to that. Okay, apply it. Now, what will it do? It will polarize atoms of that substance. Suppose polarization is P1 here. If the same electric field is applied in a different direction, same, that means this and this, they are equal. And if you apply now the same electric field, E2 is equal to E1, in a different direction, then polarization in that direction need not be same as this. Polarization may be smaller, P2 smaller. This means that polarization depends upon the direction. Even though electric field is same, polarization is not same. It depends upon direction. Whenever there are such things in physics, there is the emergence of tensors, the concept of tensors. Now, let's see here. What is the net polarization? If we apply both fields simultaneously, net polarization will be, of course, by a simple parallelogram law, it will be, let us calculate it. This will be net polarization. And what about net electric field? This is net polarization, net electric field. Since this electric field is equal to that electric field, net electric field will be at an angle of 45 degree. This is the net electric field. What do you then observe? We observe that the polarization in the substance is not in the same direction as electric field. Now, suppose now we now turn the tide like this. Suppose you have x component of electric field, an electric field in the x direction, and you apply it to a crystal. It is not must that the polarization in the crystal will be in this direction. That of course will depend upon the direction in which the bonds can stretch or compress. Now, suppose we turn the crystal, we don't keep crystal like this, x parallel to this, y parallel to this, z parallel to this. We don't keep it like that. We actually do one thing. Suppose we turn it with respect to the axis. Then, if you apply an electric field in this direction, polarization may be in this direction. This is the polarization in this direction. But if polarization is in this direction, this polarization itself will have x component, px, py, if it is in the plane of the sheet. But if it is in space, then it will have a z component. What about these components? All of them are due to Ex. Px is due to Ex, Py is due to Ex, Pz is due to Ex. Not that Px is due to Ex, Py is due to Ey. I have not applied a vertical field at all. Now therefore, we can write Px is equal to Ex. Constant of proportionality, of course, we have to supply alpha. I will write alpha x. What it means, alpha x. The first x gives the direction of polarization. The second x gives the direction of electric field. X. Now py, polarization in the y direction, that is also created by Ex. And we write it is constant of proportion, has a different value, so we cannot represent it by xx. We have to write it yx. Why? Because this x, because of this. And then pz is equal to, again, if it has a z component, then it is ex, again due to ex, and then it has zx. So these are the components of polarization. Now, similarly, suppose now you use, and this was polarization due to Ex. That is clear from this Ex. Now another group. Suppose now I apply electric field in y direction. This is electric field in y direction. It is not must that the polarization will be in the same direction. It may be, suppose for example, in this direction. This is the polarization, and that can be resolved into components. This is x component, px, this is py. Similarly, you can think of pz. So once again writing px is equal to, you have ey now. This px is due to ey, not due to ex. And you have alpha x, y. X because of this, y because of this. Similarly, you have py is equal to alpha, ey, alpha y, and pz is equal to alpha z, y, ey. Lastly, you have ez. You can have then another choice, that is ez. Ez, and you have Px due to Ez, Py due to Ez, Pz due to Ez, and supplying constant of proportionalities. Here you have alpha xz, here you have alpha yz, you have alpha zz. Now, X polarization can be due to X electric field, but can also be due to Y electric field. Look at this, look at this. This is X polarization, this is X polarization. But this is due to X field, this is due to Y field, and this is due to Z field. The total X polarization can be sum of the three, not vector sum. They are scalars now. Px is itself a scalar. Now you have alpha xx, so far as due to X field, due to Y field, due to Z field. Now when you say due to X field, you have alpha, here you have X, this must be X. Now due to Y field, alpha, this is X, this must be Y. Due to Z field, alpha X Z. Hope that you understand it quite easily. Py is similarly, it is due to Ex plus Ey plus Ez, Pz is equal to Ex plus Ey plus Ez. We now need to supply these constants. Alpha here, Yx, alpha yy, this y, alpha yz. Then you have here alpha zx, alpha zy, alpha zz. Now we can write these set of equations can be written as in matrix form. You can write it as Px, Py, Pz is equal to alpha xx, alpha xy, alpha xz. Then alpha yx, alpha yy, alpha yz, alpha zx, alpha zy, alpha zz, E1, no, not even, Ex, Ey, Ez. Now, what is this? It is an array. Array of what? Array of numbers, but with 2 dimensions. This row, and this is column. You need 2 indices to show this, any one among them. You have to show it. It says, suppose for example, you will write ij or ji, whatever you like, whichever way you like, alpha ij. Now I and j, you need 2 indices. The first index that runs over x, y, z, but in the first row it is constant, I is constant, x. It is j that changes, x, y, z. Similarly, in a column, j is constant, x, and I changes. So you need a quantity that has 2 indices, unlike components of a vector. This is then the example of a tensor of second rank. You can tensor of second order. Tensor of second order. SOT. Second order tensor. SOT. Now you have in this second order tensor, it has 9 components. 1, 2, 3, and these 9 components. First order tensor, which is the vector that has only 3 components. It has 9 components. And this number of components goes increasing as the order of the tensor goes on increasing. Now we can write a particular component, say P jth component can be written as sigma, jth component say x, can be written as sigma alpha, you see alpha, and you have here alpha, and here you have ex, just I will neither write x here nor here. I will decide it. What should I write here and what should I write here? Now let us see. I'm talking of only one component. For example, this. In this component, I am demanding j component. That means my first index is j. My first index is j. Now this first index is preserved throughout. So this will be j. Good. Second index, that is x, y, z, that changes. Second index I changes. This is the jth component. We will require this. I will request you to remember this. Please remember this and understand it. We will now turn to another example of a tensor, that is stress tensor. Stress tensor. You are familiar with intermolecular forces. Suppose you have a solid substance. This is a solid substance. Say a ball. Internally, it is composed of molecules or atoms. These dots represent its constant particles. That means either atoms or molecules. Now, these atoms and molecules, they can attract and they can repel. Depends upon. If you push two atoms beyond a certain distance, you make them come closer. Beyond a certain distance, they will repel. And if you take them away beyond the same distance, they attract. So suppose there is a solid, someone is pulling it, it is under extension, its atoms will be attracting each other. They just don't want to go away from each other. And if it is under compression, these atoms will repel in order to overcome that compression. So anyhow, atoms of a solid, they not only solid, gases, solid, these liquids, but we are concerned here with solids. Atoms of a solid, they exert forces on each other. Suppose you have a cross section through this. This is a cross section. It is not a line. It is a plane across this, and there are atoms to its right, and there are atoms to its left. Now these atoms will attract or repel. Suppose these atoms here, they repel these atoms. The atoms on the right side. This force basically shows us atoms on the right side, they attract atoms on the left side. Similarly, you can have it as corresponding this pair minus, if it is F, this is minus F. So across any cross section, at any point in a solid, there are forces. These forces, even though they are in equilibrium, they create a kind of this tension and stress within the solid. Now suppose we look at this stress more closely. Suppose we have a solid in cubical form like this. We have a cube. Then we orient these coordinate axes in such a way that this is x-axis, this is y-axis, and this is z-axis. Okay. Now, if we look at this face of the solid, this face, yz plane, this yz plane, the area of this plane is perpendicular to x-axis. I will show it here separately. This is the plane area, and this depends on this is perpendicular to x-axis. This x-axis. Now, area is represented by orientation of an area is represented by its normal. If I draw a normal in this direction, the normal of this area and x-axis, they are parallel. Okay. Now, if we consider a small small say patch of area on this surface like this, small patch such that its area is, this distance is z, so this will be suppose delta z, and this is y, so this will be delta y. So area of this is delta y, delta z, delta y, delta z. I will show you now this patch here, and its area is delta y, delta z. Now on the right hand side, on its right hand side, there are atoms. On the left hand side, there are atoms. These atoms are pulling on each other. Suppose the force on these atoms is directed like this. Let us call this force F1. Let us call it F1 because we will need more these such forces, and we have to count them as F2, F3. Now we have F1 here, force acting across this. This is intermolecular force. Now this force, of course, it is quite easy to understand that this force must be directly proportional to the area over which it acts. Because we know greater the area, more will be molecules, number of molecules that this patch will contain. So more will be these intermolecular forces. So you have F1 directly proportional to this area, delta y, delta z. Okay, now, but if this is x-axis and this is y-axis, that is, this is x-axis, this is y-axis, then this F1 has components. It has an x component, fx1, it has a y component, fy1, and it can have a z component. So we can resolve this F1 into three components. One is F1, fx1, fx1 that acts in this direction, fx1 directly proportional to delta y, delta z, area of this is delta y, delta z, fx2 directly fy1 we will call this fy1, that is directly proportional to delta y, delta z, and fz1 directly proportional to delta y, delta z. All the three act on this area, but there is a difference. Fx1 acts perpendicular to the area, it is pressure, we call it pressure, and these two act parallel to the area, fy1 and fz1. Fz1 will be in this direction, parallel to z axis. That also acts this parallel to the area. So these two are called shear forces. They are called shear forces, and this is called normal or pressure force. Pressure. Okay, now we will have to introduce constant of proportionalities for them. Fx1 will be equal to, let us denote that constant of proportionality by s, and on that s we keep first this x and then x. Now the question is, which second x from where? Second x from where? I'm sorry, it is delta y, delta z. Second, see, this first x comes from this. It means which component of force it belongs to. It belongs to x component of force. What about the second x? Second x tells you that this area is normal to x-axis. This area is normal to x-axis. So this gives direction of area, this gives direction of x component. Similarly, you can write fx2 is equal to, fy1, is equal to, again the area is delta y, delta z, and you can write s x fy x. Again, the area is perpendicular to x-axis. fz1 s z x, area is perpendicular to z x-axis, delta y, delta z. Similarly, we can have this fx1, fy1, fz1. If we now choose This patch of area that I chose parallel in YZ plane. Here I chose it in YZ plane. Suppose I choose it from in this plane, in this plane. Across this plane as well, there will be atoms on the upper side, atoms on the lower side, and producing these stress forces. We will write it Fx2. The total force. So the total force is this F2, and we will then resolve that F2 into components. X component F2, Fx2, Fy2, and similarly Fz2, Fy2, Fz2, Fz2, Fx2. That is Fx2 will be now area. First of all, area. This area is in the. This is x. This is z. XZ plane. XZ plane. That means it is perpendicular to y-axis. XZ plane. Since it is in XZ plane, so it will be delta x, delta z. Now here you will have s, x. This is perpendicular to y-axis, hence y. F similarly, Fy2s. X, I have once again delta x, delta z, delta x, delta z, and I have y, and then I have y again, and f z3, z2, that is s, delta x, delta z, and you have s, y, z, and y. Once again you have three constants of proportionality. These three constants of proportionality. Once again you have in them you have Fy2, the only which is normal to the area. You can check it here. Fy2, that is normal to the area because it is like this. The other two are shear forces. Look at this. Remember please, the normal is normal part has both these indices same. Both indices same. Now, lastly, if you take now, we first took xz plane, yz plane, then we took xz plane. We now have to take xy plane. If the area is chosen from xy plane, you will have delta x, delta xy plane, delta x, delta y as the area, and you will have fx3 will be sx, and this, since this is perpendicular to z, it will be xz. Fy3, that is sy z, delta x, delta y. Lastly, fz3, that will be zy z y, delta x, delta y. Now, if we write them in this form, no, sorry, first let us do one thing. Suppose now I add up all the x components, x forces. Fx1 is equal to C. Fx1 is equal to Sxx into this area. Delta y, delta z. Fxx, Sxx, delta y, delta z, plus then again x component. Here, this is the x component. This Sxy, delta x, delta z, Sxy, Sxy, delta y, delta z. No, Sxy, this is this, delta x, delta z. First is okay. First is delta y, delta z. Now second is delta x, delta z. Sorry, delta x, delta z. Third is now plus. Then you have third fx3, z, delta x, delta y. Or we have one more choice. We can write it as AX means area perpendicular to x-axis, area perpendicular to y-axis, area perpendicular to z-axis. Okay. Then similarly, we have Fy1, Fy not 1, Fy total this. That is equal to Fy is equal to Fy1, Syx, delta y, delta z, delta y, delta z, Syx, delta y, delta z. You can yourself write now the second term for it. It will be Sy. Now let us be careful. Y2, Syy, Syy, and then delta y, delta z, delta y, delta z, delta Fy2, delta x, delta z, delta x, delta z, plus lastly Sy3, Syz, delta x, delta y, Syz, delta x, delta y, and we have then Fz. Fz is equal to Fz first, Fz1, Szx, delta y, delta z. The area here, you see, this area is same. Fz is equal to, you can write the rest of it. You can easily write Szx. Since the area is perpendicular to x-axis, it is x, delta y, delta z. Then you write this second term, S, Z will come from this z. Now the second, since it is perpendicular to y, you will have y here, and then you have delta x, delta z, and the third will be S, z, then delta x, delta y, that will be perpendicular to z axis, so it will be z, delta x, delta y. If now I write this in matrix form, I will have fx, fy, fz, fx, fy, fz, and I will have then first let us collect these. fx1, sxx, sxy, sxz, sxx, sxy, sxz. Now you see x remains constant, row is constant, row index constant, column index changes. Now row index here must be y, x, y, 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 z. Similarly here, s, it is z, x, z, y, s, z, z. And you have here a, which a is here with this ax, ay, az, ax, ay, az, az. The important thing to note is that this array is a tensor. It is called stress tensor because it is needed to describe stress within a solid due to intermolecular forces. Stress tensor, and perhaps the most important thing that we will need from this is that look at the diagonal elements, sxx, syy, sz. These diagonal elements represent normal forces, pressure forces, and these off-diagonal elements, they represent tangential forces or parallel forces, shear stress and normal stress. Thank you, dear students. We are now in a position to handle Maxewell's stress tensor. That will now be quite easy for us. That will be in next video. Thank you.